Hi everyone, my name is Fouad Ali. I'm a mechanical engineer specializing in fluid, thermal, and stress analysis for in continuous casting systems for the steel, aluminum, copper, and precious metal production industries. Um, my project here, what I'm doing is, and first of all, let me level with you. This is like my third time recording this, and I tend to talk too much and go over like 10, 15 minutes, so I'm going to try to breeze through this as fast as I can. So anyway, what we're doing for this project is testing the viability from an exergy destruction standpoint of passively cooled workstation systems. And so what we're doing is we're comparing three different types of cooling systems for for three different types of computers. Um, what's going on here, basically? Um, you have this very large organization, not the place I work for. This is for a buddy of mine. I'm kind of doing this for him as a favor. Um, he works at this very large organization that has lots of offices and lots of computers. And what they're looking to do right now is either upgrade the old computer systems they have right now, or replace them with something else. My buddy, here's their current system now. My buddy is proposing that they replace it with a smaller Intel NUC, which is, along with being more energy efficient, it's powerful enough that one of these can replace two of these systems. Why this is important is each employee right now uses about two computers for the sake of this study. It's two computers per employee, just because the nature of their work requires that they have two desktop environments. With this guy here, it's powerful enough that it could replace, two of them. You could run a virtual machine. Um, what I'm telling my buddy is, hey, I'll gladly do the study. However, I recommend to him that he should also propose this system as well, because this right here is basically the same exact computer as this one, as the Intel NUC. This is Alucia's R50, which internally uses the same processor and motherboard. It basically is an Intel NUC. They literally bought this system, took off the case, took off the fan, and stuck on this big giant heatsink. That is the case. And the difference is, obviously, you can see it doesn't have a fan. It's passively cooled. It's a much larger heatsink than this one. See how tiny this is right here versus this one, which is way bigger. But the idea is that for the sake of this study, not having to move as much air as fast effectively means you're generating less exergy destruction. So that's basically what we're doing for this study. We're kind of just, unfortunately, because of the lack of available data. For example, there's plenty of websites and papers and whatnot that publish thermal and energy use data on processors, but not so much on specific types of RAM, specific types of motherboards. And without having these three systems in front of me on a table hooked up to thermocouples, I really don't know what the specific energy draw is of each of these. And all I can really do is just calculate based on typical values. The processor is a different story. On the other hand, lots of data exists on that, so it's pretty easy to calculate what's going on there. Number two, really, most of the energy used in most workstations, especially these ones, I'm trying to go to the right page here, is happening on the processor. And I'll tell you why. Okay, these are enterprise systems that have integrated graphics cards. They have all the important motherboard drivers and all that on these relatively modern processors are inside of the processor itself. Therefore, the motherboard itself is not generating that much heat. And then number two, enterprise systems in general tend to be much more efficient. They're not like, for example, consumer grade or gaming or any of that, where no one cares how much juice those suck up and how much energy they put out. Enterprise systems are pretty efficient. therefore, you can. What am I trying to say? Most of what's happening as far as energy is happening in cooling the processor. Is what I'm saying. Is the heat going in because of the processor and the heat coming out because of the cooling system. That's I would for this I would estimate it's between like 80 to 90%. And so if you're able to calculate the exergy destruction of that of this right here, that's probably most of what's going on with the system, and it's a pretty fair assumption. Let's see. Speaking of assumptions, for our model, we're going to assume that at any one time, this is a steady state analysis, that at any one time we're under about 50% load, that our heat sinks are completely symmetrical, that they're material-wise completely homogeneous, they're thermally homogeneous, they're in a dust and humidity-free environment, 100% efficient. We're also going to ignore any effects by these are systems that utilize, these are heat sinks rather, that utilize heat pipe technology, which is pretty cool. I highly recommend you Google it. It's pretty neat. Basically, with heat pipe cooling, what you have is, you have your regular copper pipes, but inside there's a small compartment that's filled with a combination of fluid and gas. And what this system does is it takes advantage of the fact that you need a particular amount of energy to transform this liquid that's inside of this compartment into a gas. And then to transform the gas back into a liquid. It takes advantage of that and actually increases the cooling capacity of the system. It's pretty neat, and this particular method of cooling is actually found in a lot of small electronics and things like that, and a lot of computers too. Unfortunately, for the sake of this study, we just have to ignore it. It's also, if you look back at this diagram, it's already kind of assumed in this model anyway. I mean, like, you don't, why calculate phase change if you don't have to for something pretty simple like this? Oh, this says 2D model. This is wrong. It's just a one-dimensional modeling. So ignore that. It should say 1D. Let's see what else. Okay, so 1 second. I'm gonna get a drink of water here. Thank you. All right. So what we also had to do is we had to assume that the exit air temperature cannot exceed 32 degrees, and there's kind of a neat reason why this is. Some of you who are already experienced in the industry, you already know this, but for the most part, products that are meant to be used in what's considered a non-dangerous environment, like inside of an office or inside of a well-monitored factory or any of that, typically they don't like the surfaces. Most regulations around the world, whether it's consumer, OSHA, union, whatever, they don't like the surfaces of particular objects that users use. They don't like the surfaces to exceed 90 to 95 degrees Fahrenheit. This is kind of the norm across most industries. And when they're building computers, this is also what they do as well. They make sure that the exit air temperature doesn't exceed 32 degrees. And so we have to make that assumption. How this affects our energy problem is that we're going to have effectively two mass flow rates. Okay, one is going to be a minimum mass flow rate, and then the other one is going to be a desired mass flow rate. In other words, the minimum amount of air that you need to keep your exit temperature, at or below 32 degrees Celsius. This is just done for the two forced convection problems, not for the passively cooled computer, because its temperature is what it is. All right. Let's see. So again, I didn't have these systems in front of me. I didn't have these components in front of me. All I had to do was kind of do the best I could to get the measurements of these, and then based on relative fin thickness and what the measurements are, kind of calculate what my effective heatsink area was. From there on, we were able to get our convective heat transfer number. We had to subtract our effect of radiative heat transfer out of this. Calculate our minimum air velocity, our desired air velocity, and from that point on, we could then calculate our exergy. So looking at our results, we this is just of the cooling system itself. Um, you know, from what you can tell, it doesn't look initially like too much of a difference. I mean, going from the proposed system back to the current one, you only get a savings of like 0.25 watts of exergy destruction, and then again, going from the passively cooled system to the proposed, it's still like half a watt. However, keep in mind that there are about 260 workstations currently in this office, and there are 30 identical offices in this organization. So doing the math there, and remember, we can, if we go with either the second or third proposal, we can replace, we'll only need half the amount of computers. So if you look at the amount of exergy, generated, and how much you're saving, it's pretty significant. And then, I mean, I also did some additional numbers here as to like how many additional computers you could buy just with the exergy destruction that's going on. Now here's the neat thing. I'll cover this. How much? Oh yeah, wow, we're up to 11 minutes. Okay, so here's the cool thing. This isn't some pie in the sky, recommendation. You can use one of these systems right now. Any computer system out there. I mean, next time you're walking around, you're going through a library or an office or anything. I mean, look around. If you see a computer, chances are it's what you would consider a light to medium load computer. It's not doing video processing. It's not doing 3D gaming. You're not playing the latest Fall Cry or Call of Battle or whatever, on it. Something that generates a lot of heat. No, you're not doing that. You're working in Microsoft Excel and surfing the web. These aren't applications that generate a great deal of heat. Neither are the let's say the servers that that store websites or that do a lot of cloud storage or any of that. These are a lot of computers that really don't generate that much heat compared to ones that do intensive computational workloads, for example. What I'm arguing is that you could take those systems that exist right now, take the fans off them, take the heat sinks off them, and stick a larger heat sink, and that's it. They would effectively be cooled by the fact that hot things like to transfer energy towards cold things, as you know. And so it's pretty neat, and just in this organization alone, you're saving a lot of exergy, destruction. So imagine if you were to do this for, let's say, let's say a large data center, or any place where there's a lot of computers that don't do a lot of work. But yeah, so it's pretty neat. I guess a drawback, would be that, these right now these things are kind of heavy. You have to remember it's a big piece of aluminum and copper versus look how tiny this heatsink is. Look how small this one is. This is, I'm not saying big. I mean, that's not that big, but not compared to a desktop, let's say. But the expense is up there. And then, of course, anytime you're designing, systems like these from an enterprise resource standpoint, you don't want something to be too heavy because then you have to figure out the cost of transport and all this. However, what I would argue is for the systems that I'm proposing these be used on, these are systems that are bought once, are transported once, they sit there for a very long time. They're not moved that often. And so, it's added weight wouldn't play that much of a factor. The added cost, again, the fact that, you're not wasting all this additional energy you don't need to cool it, that'll pay for itself in due time. And look, guys, what I'll leave you with is next time you're sitting at home, sitting in front of your laptop, whatever, and there's not that much ambient sound going on. You're sitting there watching a video or whatever, and you hear the fan in your computer kick on. Think of that. Listen to that whooshing noise. That whooshing noise that you hear from the air or whatever. That's that's really it's what you're hearing right there is air turbulence, the whooshing part of the noise. The whoosh. Okay, that's air turbulence. That is energy that's being wasted instead of it cooling your computer. I mean, a part of it is, but for the most part, it's not. You're hearing that. Most computer fans in the world today, they're between like 14 to 30% efficient. Laptop fans are really not efficient at all. The smaller it is, the less efficient it probably is. This is why most Apple products or really high-end computer products use passive cooling actually, instead of fans. But because they can afford to as well also. But anyway, just kind of think about that. So I'm trying to think of any questions that might be asked because this is a video and I can't be around. I can't be in class today. Let's see. Okay. Hey Fouad, is this system available now? So the company that makes it, yes and no. There's a few vendors you can get this from, but right now not really. It's not being mass sold as much, mostly because, honestly, these cases are kind of heavy and kind of expensive. Because remember, this is a lot of high quality copper and aluminum that you're purchasing for this, just to get rid of a fan and a heatsink. So there's that trade-off. But here's the neat thing. So this company, Alucia, or is it Alutia? I don't know. I think it's Alucia. They're actually working on cooling components for data centers, to be used initially in third world environments, places where you don't have dust free and air conditioned facilities, but that way you can still provide internet and other important computing needs to a lot of places that otherwise wouldn't have access to those things. That's number one. But number two, they're working now on these systems to use them here. So you can have, think about anyone who works in a large data center with a lot of computers. The one thing you notice walking into those facilities is they're very loud. You hear a lot of fans. You hear a lot of wind noise. With these, that would be a lot less energy wasted, really. So that's kind of the neat thing. Again, I want to stress that this is something that's available right now. You don't have to wait for this. There doesn't have to be like a any type of additional things or research that needs to be done. These are things that exist right now. All right, what are we up to? We are up to 17 minutes. I think we're good there. All right, take care. Thank you very much. Bye bye.